Hello everybody, my name is Thomas Trautsch and we are progressing today with the proof part 1 of proposition 6 of Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And as you may remember, in the previous video we were dealing with the construction principle of the tetragonism based on the semicircular curve. And this construction principles, there were actually two of them, one of them based on the tangents of each of these points and the other one based on the secant of consecutive point pairs, which gave us both areas as a result. And the whole purpose of proposition 6, as we laid out before, is the proof of the indivisible method. And Leibniz was using basically a quite different indivisible method, namely based on these resecting figure viewpoint, as compared to Cavalieri, who introduced the so-called indivisible method. But he had another approach. He was basically putting one area and another area next to it, and he said that whenever you draw a line across both of them, and then each position of the line as you move it across the area, when there's a equal length both overlapping of the line with both of these areas, if these lengths are equal, then the areas must be equal. And what's lacking in this viewpoint was basically what is a line. I mean, if you sum up a line with another line, knowing that the line has a codimension of 0, which basically makes the sum of many lines still 0, and you would actually never get an area. So you would, in Cavalieri's time, you still would be stuck to actually moving, instead of lines, sort of finite or rectangles, finitely slim rectangles. And this problem got only interesting once John Wallis from England in the late 17th century introduced the concept of the infinitesimals by saying that there is a dimension which has a quantity of 1 divided by infinity, 1 divided by an infinitely large quantity. And this is what Leibniz picked up on and had a very elaborate view on these things, especially in this work of the quadrature of the circle. But for now, in proof part 1, in order to get to what we just mentioned, for the purpose of proposition 6, he needed to show first of all what the concept of the resecting figure is, and what the nature of the resecting figure is in terms of continuity, and hence we can derive some information from why the resecting figure is actually called the resecting figure. For that purpose, we start looking at, for instance, one of these little segments. Let me make this a little larger. We basically place 2 points on the curve, and we look at a single segment like this. So area 1 like this, which is later be called elementary rectangle, or the red area 2 like this, which is later called the quadrilinear area. And we look at one of these things and how are things related there by looking at 2 points only. So we place point C1 and C4, and we make our little tangent based construction. The tangent of each point intersects the conjugate axis, a vertical dropping from there, which again intersects the ordinate of the appropriate point, and this intersection would be called D, and the appropriate numbering based on the originating point. The same we do for the secant construction. We draw the secant, the intersection point M2, draw the vertical. The vertical will intersect with both ordinates of both points, and the first one we named N1 and the second one P1. And this allows us now to define dimensioned areas. So we have the elementary rectangle as part of a stair-shaped figure if you place more than 2 points on the curve, and the quadrilinear area, the red one, which are subsequent to the tangent constructional rule producing the D points. And in the next step we are moving these points around. So and see what happens. The secant is moving, the appropriate tangent is moving, and we can state right from the beginning there, as no matter what point I move where, it is always the case that the secant of these 2 points intersects the conjugate axis always in between the points T1 and T4. And this is a major part of the reasoning why the resecting figure, which we shall have a look at in a moment, is actually named resecting figure. So that means that the vertical from originating from point M2 is always falling in between the verticals of the points T1 and T4. Alright, which also bears the consequence that the intersection points of D1 and D4 and the line N1, P1, which is a point we name F, is always falling in between the bounds of this rectangle. So no matter where or how I place these points, this will always be the case. So now Leibniz was considering something in terms of the continuity. But first of all, let's draw out the resecting figure itself. And how this is done is basically we take this point C1 here, start at the apex point of the circle and have it moving down the entire semicircle. And what we do when we do this dynamically, we just trace the D1 point continuously and draw out the subsequent curve. And that's what we're going to do now. The resecting figure is drawing out in red now. And there we go. So, and as you can see, and which seems actually quite logical, is that when you have a construction principle like this, which is based on an originating figure which has a continuous curve, the subsequent curve must also be of continuous character. And now Leibniz was assuming an example which is actually impossible, just to demonstrate what is never going to be the case within a resecting figure that is a product of a continuous curve like the semicircle. He said that, okay, let's assume the resecting figure is not going continuously its path like this, but it's making a bend here and taking a road here and maybe also going down here, basically circumventing this rectangle which I'm framing here right now, which is later being labeled the complementary rectangle. And he said that due to the continuity or the continuous character of the originating figure being the semicircle and the construction principle, would not allow the resecting figure to have any discontinuities, like here. It doesn't stop here and then suddenly go upwards. That's not possible. And what the resecting figure never will have either is reversion points. So that means points like K or like Q, where you have an apex of a path basically circumventing this complementary rectangle. That's not possible. And he was just showing that to make sure that we know that the resecting figure bears its name, because it's always bisecting this line from M2, which is falling in between the ordinates. So the resecting curve is always intersecting these vertical from M1 right between the ordinates of both points. So it's always falling, this intersection point F is always falling in this complementary rectangle. And he also gave a definition of what reversion points actually are. And he said that reversion points are basically points in which the tangent of these points becomes equal with the ordinate. Basically what we would call today a maximum. And that is what the part one of this proof is actually the state. If we summarize it, we have a continuous originating figure being the semicircle, and by means of the construction principle we thus are only able to produce a continuous curve called the resecting curve as a product of this construction principle. And it's not going to be discontinuous, and it's not going to have any reversion points. And that is going to become important consideration for the following parts of the proof of proposition 6. So I hope that clarifies some things for the later considerations, and I hope you stay tuned for the next video, being part 2 of the proof of proposition 6. Thank you very much, and bye bye for now.